Today we're going to talk about limits for trig, exponential, and logarithmic functions. By the way, remember that you have a quiz on Friday. It's through the first 3 worksheets. Your test next week will be through the first 4 worksheets. So today we're actually starting the next unit, okay, in terms of tests at least. So, we're going to look at something called the squeeze theorem. Some books call it the sandwich theorem. It's the same idea. Suppose that for all x in an open interval containing c, except possibly at c, again, we don't care what happens at c when we're looking at limits as x approaches c, that g of x is always in between or equal to f of x and h of x. Then, if the limit as x approaches c of f of x and the limit as x approaches c of h of x is equal to L, then the limit as x approaches c of g of x has to be L also. So basically what we have here is, and you don't need to draw this, you've got f of x is down here, g of x is here, and h of x is here. Except at some point, this top function and this bottom function are going to the same place as we get close to c. Well, that means it's got to look something like that, right? And this other one has to be in between. It gets squeezed to that point. Or that's why it's called the sandwich theorem. It's 2 pieces of bread. You know, the stuff in the middle gets trapped in between them. I think the squeeze theorem is actually a better name for it because it actually squeezes it all the way down to that one point. All right, so how does that help us? Well, that helps us with things like this. Find the limit as x approaches 0 of x times sine of 1 over x. This is a weird little function because as x goes to 0, well, that's going to go to 0, but this is going to be oscillating all over the place, right? It's going to, but there's a limitation to its oscillation. What is sine of anything always in between? What 2 values? What are the upper and lower limits on the sine function? What's the lowest? See, this is not great, guys. Thank you. All right. So, since -1 is always less than or equal to sine of 1 over x, which is less than or equal to 1, multiplying all parts of that by x to get this function in the middle, we get negative x is less than or equal to x times sine of 1 over x is less than or equal to x. Notice you do have to be a little bit careful on this because this is only true for x greater than 0, right? If you've multiplied, and I guess I could include equal to, if you multiplied by the other way, it would switch all of your inequalities, okay? But if you switch them because it's going to squeeze, it's fine. So if I now take the limit as x approaches 0 of negative x, that's equal to 0, and the limit as x approaches 0, and I'm using 0 because that's what we're looking at, of x is 0. And this function is squeezed in between the two. Therefore, the limit as x approaches 0 of x times sine of 1 over x is also equal to 0. When we're doing functions like this, most of the time it's going to be sine or cosine because we can easily bound those. Right? It's helpful for showing this. Now, if you just are asked this and you don't have to justify it, my internal process is, well, x goes to 0, sine goes to something, but it's only in between -1 and 1. And it's taking on all those values, but this is going to be really close to 0. So those values don't really affect it very much. Okay? That's how I informally reason it out. To formally reason it, you got to use the squeeze theorem. All right, so a reminder, I think we did this earlier, right? The limit as x goes to 0, sine of x over x is equal to 1. Have we done that?
I think so.
Okay, I'm pretty sure we did. We graphed it to look at what the limit would be.
It was a semicircle, right?
No,
Something else.
that was the square root of 4 minus x squared.
Right, that's the other important one.
If we graph y is equal to sine of x over x, I'll start with a zoom standard. We'll find it's way too small to really see things very well, so I'll zoom in. You can see that this function goes to 1. Notice if I trace it, at 0, there is no y value. But if I go to either side, it's incredibly close to 1. Okay? This is something that you should just memorize. We did that in class early on to talk about how you could look at a graph to help you find a limit. This is something you need to have memorized. Okay? All right, so if we want the limit as theta goes to 0 of sine of 3 theta over theta, notice this is not quite the same because the argument on sine up here is x and its denominator is x, but here the argument is 3 theta and the denominator is not 3 theta. They have to be identical. Well, you're like, okay, I'll just multiply top and bottom by 3 then. So I'll have the limit as theta goes to 0 of 3 times sine of 3 theta over 3 theta. Now this part, as theta goes to 0, that goes to 1. So this limit is 3. Cool? All right. Let's establish that the limit as theta goes to 0 of cosine of theta minus 1 over theta is equal to 0. We're going to just do that graphically. So I'm going to go back to here. Delete that. I want cosine of theta minus 1 over theta. All right. And we could also do a table for this, right? But it's the graph itself is pretty convincing what I sometimes tell people, if, because occasionally graphs totally lie to you. There's hidden behavior that you don't see. I'm like, well, if you're suspicious at all, zoom in a couple of times on the point where you're interested. And when it gets to the place that it just looks like a line, then you're probably good. Okay? This is another one that you should probably memorize. The other one is way more important, but this is a good thing to know. That the limit as theta approaches 0 of cosine of theta minus 1 over theta is equal to 0. All right. So now we get into all the wordy parts. All trigonometric, exponential, and logarithmic functions are continuous on their domain. Therefore, if y equals f of x is any trigonometric, exponential, or logarithmic function, and c is in the domain of f of x, then all we have to do is a straight up substitution. The limit as x approaches c of f of x is f of c. This is also true for inverse trig functions, any place on its domain. Now, let's quickly talk about the domain of various functions that you may have forgotten. Sine, cosine, exponential functions, inverse tangent, and inverse cotangent. And you're like, I don't remember what inverse tangent or inverse cotangent looks like. I don't very well either, but they're kind of look like, they're topped, bottom and top by negative pi over 2 and pi over 2 for tangent, and it goes through 0, 0. They're continuous for all real numbers. Now, tangent and secant are continuous except for odd multiples of pi over 2. Pi over 2, 3 pi over 2, 5 pi over 2. Those are all places where it's not continuous. Cotangent and cosecant, same except for its multiples of pi. Inverse sine, inverse cosine have a restricted domain. It's from -1 to 1, which when you think about it makes sense because the output of sine and cosine are restricted from -1 to 1. So since the range of sine and cosine are -1 to 1, the domain of their inverses is from -1 to 1. And then log functions, inverse secant, inverse cosecant are continuous for x greater than or equal to 1. Again, that's the range for secant and cosecant. So that becomes the domain for the inverse function. And then the log functions are continuous for x greater than 0. Remember, log functions don't exist at 0. We cannot take the log of 0, nor can we take the log of a negative number. So let's look at some limits. Don't have to go through quite as fast as I thought. So here, we're looking for the limit as x approaches pi over 3 of x squared minus sine of x. Well, that's a polynomial, and this is a trig function. We can simply substitute. This is going to be pi over 3 quantity squared minus sine at pi over 3. If it's an AP exam, you can leave it like that, but let's practice a little bit of unit circle. Let's see. Sine at pi over 3 is pardon?
Unit circle has to roll away, but it'll come back sooner rather than later. It has to.
So this is something where you need to get to the place where for unit circle, especially in the first quadrant, I mean, I'm not even asking you, some crazy fourth quadrant value or something like that. You need to be able to come up with those within a second or two. Okay? I personally use the hand trick. Okay, I learned it years ago, and it's way faster than me trying to think about, well, what does the graph of this look like? So if you're looking at your left palm, this represents first quadrant values, where your pinky is 0 and your thumb is at pi over 2. And it's easiest in radians, actually. It's easier than degrees. This is pi over 2, pi over 3, pi over 4, pi over 6. There is no pi over 5 in the unit circle values, and 0. Okay? The thumb side is the cosine side, and the pinky side is the sine side.
Square root of 3 over 2.
So you put down, this is pi over 3. You take the square root of fingers divided by 2, and it sounds like an awful lot, but with a very little bit of practice, you're like, oh yeah, that's square root of 3 over 2. All right, for this problem, let's take a look at what's going on here. I'm going to add to this, and I think I meant it to be on there, but when I was looking at the notes this morning, I was like, let's make that from the right. All right, so as x goes to 1 from the right, let's talk about what's going on in here. The numerator is going to go to no. I'm sorry?
Like the domain
No, what does, as x goes to 1, what does e to the x go to? This is not a trick question. Don't think about it. Don't think about it at all. What does it go to?
0?
No.
2.7.
No. Well,
X.
that's close. It goes to e.
Yeah.
E to the first is e. Right?
Yeah.
Yes, yes?
2.7.
Okay. As the x goes to 1 from the right, the denominator is getting close to what? 0. Is it a positive number near 0 or a negative number near 0? We're going to 1 from the right, so we're taking values of x bigger than 1. So that's going to be e over 0, and it's going to be a positive number near 0, right? When the denominator gets close to 0, what does the fraction get close to? What does the fraction do? Okay, everybody get out a calculator. Everybody get out your calculator. Take 2 and divide it by 0.000001. That was 5 zeros in case you didn't catch it. What kind of a number do you get?
Very large positive.
A very large number, right? When you take a value and you divide it by something that is really close to 0, that gets really big. Conversely, if you take a number and divide it by something that's really big, the fraction is really small, near 0. Those are two things that you have to know for limits. So, this is going to go towards infinity, right? And what does natural log do as its inputs go towards infinity? Yeah, it keeps going up. Incredibly, painfully, glacially, slowly. But it does keep going up. This is going to be infinity. Pardon?
We'll see if this one goes back.
All right. So, As theta goes to 0, notice my numerator goes to 0 and so does my denominator. Anytime that happens, that means you're going to have to do some sort of manipulation to that function. Note that I have 2 terms in the numerator and only 1 in the denominator. That means I can break it up into 2 separate fractions with a denominator of 3 theta. So we can rewrite this as the limit as theta goes to 0 of theta over 3 theta plus 2 sine of theta over 3 theta. As theta goes to 0, well, everywhere except at theta is 0, what's theta over 3 theta equal to? 1/3. Because theta over theta, everywhere except at theta is 0 is 1, right? And then here, as theta goes to 0, what is sine of theta over theta? Whoa, no, I'm asking just for sine of theta over theta. 1. So this is, sorry, not a plus, not an equal plus, 2/3. This goes to 1. All right, as x goes to 0, the product of x and cosecant of x. And you're like, cosecant, blah. So I don't know about you, I don't have like secant, cosecant, all those things. It's like, not real good at those. What I have to do is think about this is the reciprocal of sine, which looks like this. And so cosecant looks like this. So cosecant is going to be from the left is going to go to negative infinity, and from the right is going to go to positive infinity. And x is going to 0. Now you may go, well, 0 times anything is 0, but as a limit, this isn't actually equal to 0, it's just really, really close to 0. You can't do that like it's a number. You can't just multiply them and go, oh, that and this is infinite. If it was 3, then I would be okay with it. But not so much here. So here's what I'm going to have to do. Cosecant is the reciprocal of sine, right? So shouldn't this be equal to the limit as x goes to 0 of x times 1 over sine of x? And isn't that then x over sine of x? Which goes to 1. Yeah, we keep coming back to that one. But sometimes you have to rewrite it so you can see that it's x over sine of x.
So x over sine of x and sine of x over x are both 1?
Yes, because if one of them goes to 1, its reciprocal should also go to 1.
Makes sense.
All right, any questions? Yes.
The natural log of e to the x over x minus 1.
Yeah.
I'm just confused of how, since the denominator it's 1 minus 1, it's e over 0 is equal equal to infinity?
So if you take e divided by 0.0000001,
So it's not 0. It's just a really, really small decimal.
right, when you subtract that, yeah,
Okay.
it's going to be
Yeah.
going to 0,
To the right. That's right.
and so it's going to be a really small positive number because we're coming from the right.
Okay.
Yeah, and
Is that why you changed it to
from the right,
left
because
to
if
the
it was
right?
from the left, this would have been negative infinity, and natural log is not even defined for negative values. And that's why I changed it to be from the right.
So in our homework, are we ever going to get like something like that, or are we always going to get like to the left or to the right for natural log?
I will try not to give you ones where it's like, yeah, this doesn't work. I suppose that if it wasn't from the right, you would have to say this was infinity, and then you would have to go, what's the limit as x approaches 1 from the left of natural log of e to the x over x minus 1. This would be going to negative infinity, and natural log doesn't exist there. This part does not exist. So the limit as x approaches 1 doesn't exist because the left and the right don't agree with each other. Okay? Good question.